Hello everyone, and let's continue our lecture on linear algebra. In the previous lecture, I talked about vectors, and today's lecture is about matrix. So matrix is a set of vectors. For example, here we have A1, A2, and A3, and these are vectors based on the definition that we had already. If we bring all together in here, so A, we show matrices with capital A, and we say vector A, vector A2, A3, then we have a matrix here. So with vectors, we can represent single variables as set of numbers or instances. With matrices, we can represent set of variables. A matrix is officially defined as a mathematical structure that consists of an ordered set of numbers or elements that we arrange them in rows and columns. So this is one row and this is one column. So it's typically represented by capital letter, and we can use them and we can apply different operation. We have too many kinds of matrices like basic matrix, cofactor matrix, diagonal matrix, elimination matrix, Fourier matrix, Hadamard matrix, identity matrix, Jordan matrix, and many others. If a matrix has m rows and n columns, then we show it m by n, where m is the number of rows. For example, here we have 2 rows, here we have 3 rows, and n is the number of columns, 1, 2, 3 columns, 1, 2 columns, right? In a square matrix, later I will show you, a square matrix, it means the number of rows and the number of columns are the same. For example, 2 by 2 or 3 by 3, right? And we show it like m as the name of the matrix and m the number of rows and number of columns, right? So for example, here we have 2 by 3 matrix, we show m 2 by 3, and here we have 3 by 2, right? We show it like this, m 3 by 2. Index of components. In order to access the components of a matrix, we show for index of components, right? If we consider I as the row number and j as the column number, then we say, for example, 1 and 2, right? 1 and 2, where in here is the first one is 1 and 1, second is 1 and 2, third is 1 and 3, up to last one, 1 and n. In here is the, for example, 3 and 1. It means this minus 2 is the component in row number 3 and column number 1. This one is 3 and 3. It means row number 3 and column number 3. So if we have 2 matrices which are in the same size, it means both rows and columns, the number of rows and the number of columns is the same, then we can add them or subtract them, right? And we also can multiply by a scalar. For example, if we have A and B here, right? So we have matrix A here and matrix B here, we can do A plus B, right? So A plus B, it means 1 plus 6 is equal to 7. 4 plus 9 is 13. 2 plus 8 is 10. 5 plus 0 is 5. 3 plus 9 is 12. And 6 plus 2 is 8. We can do subtraction. It means A minus B. So 1 minus 6 minus 5. 4 minus 9 minus 5. 2 minus 8 minus 6. 5 minus 0. 5 minus 0. It should be 5 plus 5. 3, 9, and 6, 2, 4. We can do scalar multiplication. It means one scalar, one real number multiply a matrix. So 9b, it means 9 multiply all the elements of B. So 9 by 6, 54, 9 by 9, 81, 9 by 8, 72, 9 by 0, 0, 9, 9, 81. And so this is how we can do scalar multiplication and matrix multiplication and subtraction. Zero matrix, in some applications, we have to initiate a matrix with desired size. Then we store our output like zero vector that we had. So zero matrix where all elements are zero, and we denote by O. You can see here. So O or O, it means this is M, and N is the size of this matrix. For example, O2 and 3, it means 2 rows and 3 columns. In this case, A plus O, it means A. So A means any matrix plus zero matrix is itself. Zero matrix multiply A is zero matrix, and A minus A is always equal to zero matrix. The next one is identity matrix. Identity matrix is as a square matrix where diagonal are 1, right? You can see here. It means A, I, and J, where I is equal to J. A, I, and J. It means 1 and 1, 2 and 2, 3 and 3, 4 and 4, all are 1, right? This is how we can call it as identity matrix. So here are the properties of matrix. If we have three matrices like A, B, and C, we have three matrices A, B, and C, and these are m by n matrices, and we have S and T as our scalars, then these are different properties of matrices that we have. The first one is matrix addition, which is commutative. Commutative means A plus B, matrix A plus matrix B is always equal to plus B plus A. It means A plus B and B plus A is the same, right? It means the result of adding two matrices is the same regardless of the order in which they are added, right? It means, very similar to addition of real numbers. In here we have A plus B plus C is always equal to A plus B plus C. It means it doesn't matter which two are added first. So when we adding three matrices, it doesn't matter which one we add. First we do A plus B, or first we do B plus C, then the result plus A. It doesn't matter. The next one is associative property of scalar multiplication. So we have S and T, and here we say S and T are scalar, real numbers. So if we first multiply S and T together, then the result multiply A is the same. If we do first T by A, then multiply S by the result of them. So it means multiplying a matrix by a product of two scalar is the same as first multiplying one of them, then you multiply the result by that. It's the same. The fourth one is scalar multiplication distribute our matrix addition. It means if we multiply one scalar to the sum of two matrices is equal to, you multiply the scalar separately, then you sum the result. This is totally the same, right? This is called as distributive over the matrix addition. And the last one is distributive property of scalar addition. It means first you sum two scalar and multiply the result by a matrix is equal to sum of distributed multiplication, S by A, T by A, then you sum all together. These are properties of matrices. Transpose of a matrix is flipping rows and columns of a matrix. It means when we have a matrix of m by n, we change it to n by m. So here we have a matrix 1 by, this is 1, 2, 3. So this is 3 by 2. We change it by 2 and 3. It means you can see here 6 is here, 8 become to the first row, and 9 become here. Then again 9 is here, 0 is here, and 2 is here. This is called as transpose, matrix transpose. And you can see here 80, transpose of matrix A, right? We flipped the rows and columns. So if we have a matrix A with dimension of like m and n, then transpose will be denoted by A and T and will be n by m. M by n will be changed to n by m. This is called as transpose of a matrix. So these are the properties of transpose. So here we have A and B, and A and B are m and n. So you can see here, these are two matrices that we have, and S is also a scalar. So AT, it means transpose of A. It means once we flip the row and columns, then again we flip the rows. It means go back to the first version. So transpose of transpose is equal to A. Transpose of transpose is equal to A. The second one is multiplication of one scalar to a matrix transpose is the same as multiplication of that scalar to the transpose of A is the same. And here is the distributive property. A plus B transpose is transpose of A plus transpose of B. A plus B transpose is transpose of A, transpose of B, sum of two transpose. So here, let's see the example. 2A means multiplication of one scalar to A. Matrix A is here. 2A, 2 by 5 is 10, 2 by 5 is 10, 2 by 6 is 12, and 2 by 6 is 12. Then 2A transpose. It means we have already 2A, then we transpose it. So 10 will come here, this 10 will come here, 12 is here, and this here. This is called as transpose of 2A. A transpose, here is our A, so we flipped 5, 6, 5, 6, right? 2A transpose, it means we multiply 2 by here. So 2 by 5 is 10, 2 by 6 is 12, 2 by 5 is 10, and 2 by 6 is 12. A plus B means 5 and 7 is 12, 5 and 7 is 12, 6 and 8 is 14, 6 and 8 is 14, right? This is A plus B. A plus B transpose means transpose of this one, right? This become column, this become row. A transpose is this one, B transpose is this one, A transpose. So you can see that this property that we have shown it here, right? This is how it works. Matrix and vector product is the next topic. So it means here we have a matrix, and matrix is A n by n. So A, and here we have a vector. So multiplication is A11 multiply x1, A12 multiply x2, and up to A1n multiply x. This is come to the first row. Second row, A21 multiply x1, A22 multiply x2, and up to A2n multiply xn. Then we will come to the last line, AM1 multiply x1, AM2 multiply x2 up to n. This is how we can do multiplication of matrix to a vector. The same thing here. We can say for linear multiplication, we can do it, and this is a kind of linear system. A linear system means a set of linear equations that they have one or more variable. So in this case, this is a variable. This is called as variables, and these are coefficients. So the matrix will be coefficient. As you can see, A, X is variable, and B is the result. It means the sum of this one is B1. So this is kind of, each equation here is linear. It means the highest power is 1. So in here, we don't have x2 or x3. All of them are x1. So x in power of 1. We cannot have x in power of 2. If we have x power of 2, this is non-linear, right? But x power of 1 is a kind of linear. So the goal in solving a linear system is to find value of the variable that satisfy the equation. We try to find out the possible values for these variables. So here how it shows x, the variables, linear system, coefficients is a matrix, and the result will be ax. So here are the properties of matrix vector production. Suppose we have two matrices like A and B. Suppose we have two matrices A and B, and the size is m and n, and we have u and v as the vectors in Rn, right? and we have a C scalar. Then we have some properties of matrix and vectors. The first one is distributive property of matrix multiplication over vector addition. It means here we have two vectors and we have addition, then we multiply a matrix, right? It means it's distributed first, A by U, then A by V. A by U plus A by V, right? So when we multiply a matrix A by sum of two vectors like U and V, it's the same as multiplying A by each vector, then we sum them. The next one is scalar multiplication of a matrix and vector. So this C is a scalar as we had here. So C by U and then A by U is equal to C. First we do matrix and vector, then a scalar, or a scalar and matrix, then vector, right? This is how we can do it. It's the same way. And the next one is two matrix multiply a vector is equal to, we separately do it. This is called as distributive property of matrix addition over vector multiplication. And the last one is the identity matrix. This is IN by V is always equal to V, right? These are the properties. And here, if we have A and B as our matrices and their size is M and N, and if we have A, W, B, W, where A multiplied W is equal to B to W, then we want to check that whether A is equal to B or not. So the simple answer is yes, but how to prove it, I will show you. To see why this is true, let's consider a specific like W and I standard basic vector, and we denote by IEJ, and where J is the position and 0 is answer. So IEJ is AJ, and this J can be 1, 2, up to N, and EJ is the component, J is the standard vector in Rn that we have, right? Now, according to the given equation, we can say E1 that we have a standard vector that already, A multiply E1 is A that we have multiply this one, right? So we do that, A1 by 1 and the rest by 0. Finally, we will have A1, right? And then in the same way we can do for the rest, AE1 is equal to BE1. We want to check, right, whether these two are the same or not based on this property, right? AE1, then we can say from here, as we find here, we have A1, and from here we have B1. AE2, BE2. A2 will come, B2. You remember that in E2, the second was 1, 1, and the rest was. So if we check one by one, finally we can see that all the elements, all the corresponding elements are the same. And if all the corresponding elements are the same, we can conclude that A is equal to B. So here we can look at this vector and the matrix multiplication in two ways, row aspect or column aspect. In terms of, so we have one matrix here, we have this matrix A, and we have this X as a vector. So from row aspect, each element is this row is multiplied by this column. This row again is multiplied by this vector up to N. This is row aspect. From the column aspect, we can say that X1 multiply first column, X2 multiply second column up to N. So this is how you can look at row aspect or column aspect. We have Hadamard product. This is a mathematical operation that involves taking two matrices of the same dimension and we produce a third matrix. What we do here, we multiply corresponding elements and we generate a new one, right? Each element in the resulting matrix is the product of the corresponding elements in the original two matrices that we have. It is different from standard matrix multiplication because the elements are multiplied following those rules that we have. So we show like this, and so 0 multiply 1, right? It will be 0. 2 multiply 3 is 6. 1 multiply 2 is 2. 4 multiply 1 is 1. This is how we do this product. And here we have different kind of matrix. So we have regular matrix. Regular matrix, they can be different column and different number of rows, but they are not the same. If they are the same, then we call them as a square matrix. As you can see here, number of rows and column is the same, so we call it as n by n, but in here we call it as m by n. It means they are different. Diagonal matrix is where we have elements on here. These are non-zero. The rest are zero. So it means I, A, you can say A, I, and J, where I is equal to J, right? It means 1 and 1, 2 and 2, 3 and 3, they are the same. They are the same indexes. The rest are zero. This is called as diagonal matrix. The next one is upper triangular matrix. These are square matrix where the element below the main diagonal are zero. As you can see here, if this is the main diagonal, the lower part is zero, but the diagonal and the upper side can be non-zero. On the other side, we have lower triangular matrix. In here, the main one is non-zero, but the upper is zero, right? This is called as upper and lower. Symmetric matrix, we call this matrix as a symmetric because it's equal to transpose, right? It means A equal to A transpose. So if you flip rows and columns, the result is the same. The result is the same. And identity matrix, I already told you that is the main diagonal is 1. Okay, this was an introduction of matrices. So I hope you understood the general concept of matrix. It was very easy, and please you try, and please feel free to ask me your questions. Thank you.